Well, hi everyone, this is Bob the Science Guy, and today we're going to continue our review of University Physics 2, Chapter 1. Now, in the first section, we talked about heat, temperature, and the concept of thermal equilibrium. In this section, we're going to talk about thermal expansion. So if you have a look at this expansion joint in the bridge next to my head, you'll see that there's a little bit of room for either side of that bridge to expand a little bit. There's a small gap there. That's to prevent the bridge from buckling. Because when objects heat up, they tend to expand, and when they get cold, they tend to contract a little bit. Now that's going to be a very predictable value. Let's go see how to calculate that. Now the equation to calculate this is really straightforward. The final length is going to be the initial length times a coefficient of expansion, which is a linear term, times the change in temperature. Now, each individual type of material has got its own coefficient of linear expansion. When you're dealing with it in one direction, that term is called alpha. So for example, with steel, the alpha is 12 times 10 to the negative 6. And what that means is that for every degree Celsius that you raise the temperature of the substance, it will multiply the initial length of that substance by this value. So you see, it's not very much, but let's go ahead and do an example. So here we have the equation. So we just plug that into our calculator. We've got 12 times 10 to the negative 6, that's the alpha, times 10, the original length, times 30, which is the change in temperature as we increase temperature from negative 10 to 20 degrees Celsius. In other words, 3.6 millimeters. That's the expansion of the steel in response to a 30-degree increase in temperature for a piece of steel that's 10 meters long. A 10-meter long piece of steel, that's 3.6 millimeters. Now, if the piece of steel was 100 meters long, it would be 3.6 centimeters. And if it was 1,000 meters long, like a bridge, that would be 3.6 meters. That's why you break that up into several pieces. You just don't lay a single 1,000 meter long piece of steel. And this is a typical temperature change that you would get between winter and, say, summer here in Michigan. Now, the Mackinac Bridge is over 5,000 feet long. You can see that this has to be taken into account. Say we have two pieces of metal that are bonded together, but they are different types of metals. They will have different expansion coefficients. And as a result, they may be straight at one temperature, but if you increase or decrease the temperature, they may bend like this. So in addition to being important in construction, you can see how you could probably design some way of measuring temperature by putting two dissimilar pieces of metal next to each other and measuring how much they bend. But truly, there are no single dimension pieces of material to do this with. It's a nice academic exercise, but material is generally multidimensional. So for example, suppose you have a plate like this. This is in 2 dimensions. And the equation for that is actually quite straightforward as well. Now, when you're dealing with multiple dimensions, the equation is exactly the same. However, there's a coefficient that goes right here. If it's in 2 dimensions, you put a 2 in here. If it's in 3 dimensions, you put a 3 there. Now, when you're dealing with 3 dimensions, instead of using this term alpha, we use the term beta, which is equal to 3 times alpha. And actually, if you come back up to this same table where we looked up the values of alpha, we can also look up the value of beta. And as you see, it's about 3 times that of alpha. So for gold, it's 14 times 10 to the negative 6 for alpha, and it's 42 times 10 to the negative 6 for beta. 42 is 3 times 14. With iron or steel, it's 12 and 35. Slight difference, but there's probably just a rounding error. Now there's one other slight change, and that is that when you're dealing with this in 1 dimension, you deal with the initial length. What about if it's in 2 dimensions? Well, you're not calculating length then. You're calculating area final and using area initial to start with. So area initial goes here, area final goes over here. Now with 3 dimensions, again, you're not dealing with length nor with area. you're dealing with volume. And they go in the same spots. So let's do some examples. So here's an example using gasoline. The expansion coefficient, the beta coefficient for gasoline is 950 times 10 to the negative 6 per degree Celsius. And we're going to move the gas from negative 15 Celsius to plus 40 Celsius for a total change of 55 degrees. So our final volume here is going to be 950 times 10 to the negative 6 times the initial volume, 60, times the temperature change. And that's going to work out to 3.135 liters. So the initial volume is 60 liters, and the final volume is 63.135 liters. Now suppose instead we had a 60-liter gasoline tank that was made out of steel, and we had 60 liters of gasoline in it. How much gasoline would spill out if we brought that system from negative 15 degrees Celsius to 40 degrees Celsius? Now we know that the gasoline will expand by 3.135 liters, but what about the steel tank? Let's go see. And the amount of spillage is going to be the amount that the gas expands minus the amount the tank expands, because the gas is going to expand more than the tank will. And here's the setup for that. So here's our original equation. Now, here's the expansion of the fuel, the gasoline, and here's the expansion of the steel gas tank. 950 minus 35 equals 915. The rest of the equation is exactly the same. And as you see, because the gas tank also expands a little bit, the amount of spillage is going to be a little bit less than the total expansion of the gas. Now the next thing that we need to cover is something called thermal stress. And this is a very interesting problem that has a lot of practical applications. Let's have a look. Suppose we lay two sidewalk blocks right next to each other with no space in between them. There is a little bit of a gap here, but that's just to show that they're two different blocks. Now, if you lay these blocks when the temperature is cold, what happens during the summer when the temperature gets hotter? These blocks will expand. Now this is actually a little bit more of a complex problem, because when you have two blocks that come together, that's called compression force. However, if they slide next to each other like so, that's a shear force. And whether or not the concrete will break depends on whether it's being compressed or it's undergoing shear. So we're going to look at compression, and I'll show you how to calculate that. Now you may recall from University Physics 1 how to use Young's modulus. So the force over the area equals Young's modulus times the change in length over the original length. Well, we don't know what the original length was here. It's just simply not given. However, what is change in length? This also equals Young's times what? Times alpha times the original length times delta t. And it's still over original length. So these two cancel, and this becomes Young's times alpha times delta t. So Young's module for concrete is 20 times 10 to the 9 newtons per meter squared. Alpha for concrete is 12 times 10 to the negative 6 degrees Celsius. So what's happening is this is causing the concrete to expand. Young's module is forcing it back together to keep the length the same. So now we can just simply calculate this. So what we'll do is we'll take 20 times 10 to the 9th times, that's Young's modulus, times the alpha right here, 12 times 10 to the negative 6 degrees Celsius, times what? The temperature change. And I think we said the temperature change for this particular one went from 5 to 38 degrees Celsius. So delta T equals 33. And if you put that all out together, you get 7.9 times 10 to the 6th newtons per meter squared. That is a lot of newtons. However, concrete is extremely strong in compression. It is stronger than that, so it will not crack in compression. However, in shear force, it's much weaker, and as a result, it'll chip from side to side. It's an interesting problem. Now, in the next episode, we're going to start talking about heat latency and boiling ice cubes. So I hope you'll join me for that. This is Bob the Science Guy. Take care.